Okay, now that we are done with the model fitting, we are done with the hypothesis testing. It is time to do the prediction using the model. And we know we use the model for what? For two purposes. Once you have this model, once you have this model, the fitted model is this one, correct? Now, this model can be used for two purposes. Purpose number one is for a given X naught, I can ask you to predict Y naught or to estimate mu of Y given X naught. These are the two purposes for which we use the model for simple linear regression. These will be the two purposes we use the model for the case of multiple regression. Now, the thing is, for the simple linear regression, you just had the value of X. You plug it into the model and you get Y naught hat or you get mu hat. Now, this time you will have a complete row. For example, if the data is on people, their age, their BMI, their blood pressure, many characteristics of a single person, we are measuring those characteristics. So if I need to predict for a future person, I will have the values of X, all variables on that person. So this time, X naught, it will not be a value, it will be a vector. Right? X naught will be a vector. What type of vector? Let me show you. Suppose you have this data, y1, y2, all the way up to yn. And before, for simple linear regression, you had x. Let me call this now x1. You had x1, 1, you had x1, 2, and you have x1, n. You had this. Then you did what? You got a new person here, a new value here, where I gave you x naught here, right? And I asked you to predict what? Y naught hat from here. Just a single value of X naught. Let me call this X1 naught because I'm calling the variable X1. So you had a single value here. Now what will happen? You have here X2 also. You have all the way up to XK. Right? So if I give you the new observation, this new person, whoever this unit number 0 is, I will give you the information on X1 naught, X2 naught, and all the way up to XK naught. You will be given all of this. And based on this, you will be asked to predict this single value Y naught. Clear? Now, the model is like this one. To facilitate yourself in the matrices formation, you added a column of ones here while defining the X matrix. True? You will do exactly the same thing while predicting. To compensate the intercept, you will add a 1 before writing down the X naught vector. So your X naught should be something like this. It should be something like this. Clear? Now, if you want to predict, you should simply do what? You should simply put this X naught into this equation. Y hat equals X beta hat. So you just put X naught into this one and your equation becomes just put it, you'll get the predicted value. Clear? But there is a one tiny problem of notation here. Usually in the literature, you will see they call this to be a vector, but this is not a vector, it's a row, right? It's a row. And usually the vectors are denoted by a column. So what we do is, just to be consistent with the notation, it's not necessary, but this is what your book is using. What we do is, we define X naught to be a column vector, 1, X1 naught, X2 naught, all the way up to XK naught. But when we plug into the equation, we plug X naught prime into the equation, because in the equation we have to put the row. So we plug X naught prime into the equation, the transpose of this vector. so that we are consistent with the general notation of the matrices. The column vector is denoted by the original notation and the row is denoted by the transpose of column vector. So now your fitted model becomes y naught hat equals x naught prime times beta hat. Now this x naught prime will be a row, beta naught hat will be a column. When you multiply a row with a column, what will you get? A single value, a scalar value, single value. That will be the predicted value, not the, I should say that should be the mu hat of y given x naught vector, and that will also be equal to y naught hat. The point estimates will be exactly the same. Exactly be the same. Now, exactly the same story about the interval estimate. To get to the interval estimate, this is, by the way, the point estimate of mean of y when x is x naught vector. I need an interval estimate. To get to the interval estimate, I need the variance of this thing. So let us try to find the variance of this thing, which will be the variance of x naught prime times beta hat. Clear? Now x naught prime, we're assuming the x is to be fixed. It will come out of the variance by taking the square. So square, you take the square in such a way that when it comes out, the multiplication is possible. You decide what to put first and what to put second. I can take out this one like this, or I can take it out like this. Depending upon which way the multiplication is possible, you have to check the order. Which way the multiplication is possible? Which way is it possible? The first way is possible, because this is k cross 1 into 1 cross k into k cross 1. So it will be possible. Otherwise, for this one, the multiplication is not possible. So I take this one out being squared this way. X naught prime on the left side and x naught on the right side. And in between, I apply the variance of beta hat. What is the variance of beta hat? I take it from the previous derivation. It was, what was it? Sigma squared times x transpose x whole inverse. Did we derive this? Yes. We did that. This is sigma squared times x transpose x whole inverse. So it becomes this, where sigma square is the constant. I can write it anywhere in the equation. So I choose to write it at the start. And the variance becomes sigma squared times x naught prime into x prime x whole inverse x naught. Now here is a big problem. What is that big problem? The big problem is sitting right at the start of the equation. We don't have the sigma square. What is the sigma square? The error variance. And we don't have it. We replace it by the estimator MSE. So the resulting, this one is, by the way, the variance of mu hat of y given x naught. But when I replace sigma square by the estimator, the variance becomes the estimated variance. Yes. By x, same as x square. It is like, yes, it is. You do multiply and you check. Multiply and check, and you will get to understand. Like E prime E is a summation of E square. So you have MSE times x naught, this x prime x whole inverse and x naught. And this is the variance we will use to develop the confidence interval for the mean of y when x is x naught. So 100 into 1 minus alpha % confidence interval for mu of y given x naught is given as the point estimate plus minus t or z. Why t? Because I'm replacing sigma square by its estimator. So here I'll add t alpha by 2 with n minus k minus 1 degrees of freedom times the square root of the variance, which is what? MSE times times this. And this is what we will use whenever the confidence interval for. This is for the mean of y when x is x naught. Now I take you back to another derivation that we did for the simple linear regression, and I will copy paste that without any change, without a single change. This was probably week, this one here. What was the discussion? The discussion was that from the model, if you put x naught, this is what you will get, right? You will not get y naught tag, but we are saying that because we have no more information, so if we just have to guess the single value, what is the best guess? Average is the best guess. So we said that we borrow this y naught hat from this one, and we say y naught hat will be the same as mu hat. But we cannot borrow the variance because we know the variance for single observation is more than the variance for the average. So what we did is we did not take the variance directly of this quantity. We took the variance of the residual attached with this quantity because the residual attached are the single quantities. So what we did is we found the residual, this one attached with y naught hat, and we found the variance of this residual quantity. And we use the variance of this residual to develop the confidence interval. Exactly the same discussion is applicable here. What I'm going to do here is the point estimate, I'm going to borrow it by using the argument what average is the best guess. When I need a confidence or a point estimate for y naught, I will take y naught hat to be x naught prime times beta hat. Again, this is a borrowed estimate, not a direct estimate. But when I develop the confidence interval, I will not do like this. I will not do like this. Why? Because the variance of this one will be the same as the variance for the average, and the estimate, point estimate, is the borrowed estimate, not the actual estimate. What I will do here is I will plug in the variance of the attached residual with y naught. This will be my confidence interval. So the same discussion. What is E naught? It is y naught minus y naught hat, correct? So the variance of E naught will be variance of y naught plus variance of y naught hat minus 2 times covariance of y naught with y naught hat. Correct? Now what is variance of y naught? Sigma square. What is the variance of y naught hat, the borrowed estimate? Sigma squared times x naught prime x whole inverse x naught. We just derived it. Plus minus, this is 0. Why this is 0? You can justify it with the discussion also. Why it will be 0? No. Yes, this is correct. You are trying to find the covariance between y naught and the predicted value, right? Now tell me, let me take you back to this table here. In this table, y naught is not known, right? You have the x's. You have x1 naught, x2 naught. Where will y naught hat come from? It will come from this vector and this information. You will use this information to get this model, right? And then you will plug this one into this model, right? In this whole calculation, are you using the real value of y naught? This whole thing is completely independent of this actual value, which is lying over there on the left corner. So that is why the y naught hat that you will get from there, it will be based on this table plus this row. And it will be completely independent of this actual y naught. So that is why mathematically you can also prove it. That is why this covariance will be 0. And the resulting variance will become sigma square into exactly what we did for simple linear. There was a 1 plus, right? Here also you will have a 1 plus. No, it is, you can write identity or you can write 1 because this whole thing is 1 by 1. So identity will be just a 1. But you are correct, it should be identity, but an identity of 1 cross 1. Because this whole thing, if you try to see the order of this whole thing, at the end of the day, you'll get this 1 by 1. But a good observation, it should be identity. So what's the problem here again? This is the problem. So we replace this by MSE and the resulting prediction interval is what? It's y naught hat plus minus t alpha by 2 with n minus k minus 1 degrees of freedoms, square root of MSE into 1 plus x naught prime x whole inverse x naught. So just compare the two intervals. You will see we did exactly the same for chapter 2. This exact 1 plus was there. This exact 1 plus is here. Let us quickly implement this thing and see how do we get yes. F test for T test, we are creating the confidence interval. This confidence interval is coming from a pivotal quantity based on T, not F. Let me tell you, this confidence interval, those who are taking 302, they would understand it more, but this is coming from here. This is derived from here. Y naught hat minus Y naught over MSE into 1 plus x naught prime into x prime x whole inverse x naught square root. This follows a T distribution with n minus k minus 1 degrees of freedom. This thing is called a pivotal quantity. Why it is called, I'll not go into the details, but the only thing I can tell you is if you solve this equation for y naught, if you solve this equation for this y naught, you will get this interval. Okay. It comes from the T. But if you then square it, it will become F. But I don't know in case of squaring, can you solve it for y naught or no? I'm not sure. Maybe you can, maybe you can't. I don't know. Maybe you can try. Squaring it will make it F. And then if you can solve it for y naught or not, I think you cannot get a unique solution. No, it will be. Yes. Only minus. So if we solve this one, we'll get only positive or negative, one of them. Where will the second one come from? The second one will come from here. This T is sometimes, half of the times it is positive, half of the times it is negative. T is a symmetric distribution around 0. So you will get two values of T for a single alpha, one from the left side, one from the right side. The left one itself, T will be negative. So the sign will come from there. Yes. No, you don't need this one. Don't pay attention to this one. We're not going to do the testing. We never do the testing for this one. Don't pay attention to this one. We'll be using only this confidence interval, prediction interval to be more exact in terms of notation. So let us take a data set and try to find these two intervals and try to see how they differ in the width. Which one is wider? Which one is wider and which one should be wider? Of course, the prediction is wider and should be wider. Let us create a data set ourselves. So let us say we have students 1, 2, 3, 4, 5, 6 students. And Y is their overall score in the course. So let us say 80, 85, 89, 91, 86, and 82. And let us say X1 is their GPA before starting the course. So let us say 3.4, 2.9, 3.2, 2.6, 3.9, let us say, and 3.4, let us say. And X2 is, let us say, their score in major one out of what? Out of 42 or 45? 42. So 21, 26, 10, 17, 19, and 29. And let us say these are the two predictors.
Out of what?
How to
Out of what? Out of what?
plot? 42, yes. Now, before we proceed, we need what? We need a column of 1. So I'm going to add that column of 1s. A column of 1s. Then I'll denote this thing, whole thing by X. And this whole thing by Y.
So you didn't include Y.
No, I didn't include Y, yes.
Why?
Because it's not a value of Y. While defining the variables, you don't include the names. While data analysis, you do that. So my beta hat will be what order? How many values will be there in the beta hat? There will be 3. Intercept, slope 1, slope 2. So I select a 3 by 1 space. I will need X transpose X whole inverse. So I'll go step by step. First, I find X transpose X. Step by step. Transpose of X with X. First step. This is X prime X. Then I'll take the inverse of this one. This is X transpose X whole inverse, right? Then I'll find X transpose Y. This is X transpose Y. And final step is to multiply X prime X whole inverse with X prime Y to get beta hat. Let us say here I find beta hat equals. I'll multiply this X prime X whole inverse with this X prime Y. And this is my beta hat. The intercept is 106. Which means if you get 0 in major one and your CGPA is 0, you'll get 106 points in this course.
Using data analysis and
Yes.
Yes.
Because the data analysis will not give you the prediction interval and confidence interval, which I will use these things later. This one for the interval. I'll use that. Now, the first thing I'll do is I'll introduce a new student here for which I don't know the grade. So for this student, I'll compensate this one for the intercept. And let us say this student has a CGPA of 3.6. And his major one score is 31, let us say. This student, and I'll call this whole thing as X naught prime. I call it X naught P. Because we denoted this row to be transpose. We said the column is usually given the notation of the vector. The row is usually given the transpose of the vector. So the first thing I'll do is I'll find Y naught hat. This will be what? Matrix multiply this. What is the order? X naught prime is first, right? X naught prime with this beta hat. The predicted score is 79 point something. This is the point estimate. And this is the same as mu hat. This is the same as mu hat. This is the same as Y naught hat. Point estimates are same. OK. Then I do what? You can see in both of the intervals, this thing is important to find. Once I have this thing readily available, this part, I can just do addition and subtraction to get to the interval. This is the only matrix part. X naught prime times X prime X whole inverse times X naught. So I'll find this part. Let me call this part to be some function of X. Let me call this part to be f of X. So I'll find this f of X in here. So it is matrix multiplication of X naught prime with this X transpose X whole inverse. And then I'll multiply this whole again with X naught. And I don't have X naught. I did not define X naught anywhere. But I know if I take the transpose of the transpose, what will I get? I'll get X naught back. So I'll take the transpose of the transpose of X. X naught prime, another prime will give me X naught. So this is that 0.761 something, that quantity I need. So if I need the prediction interval now, sorry for the font, I forgot to increase. What doesn't make sense? No, the data, no, it doesn't. Yes, it doesn't make sense. Don't think about that. Don't think about interpreting. I just assume the data. And so if I'm interested in the prediction, I will have the lower limit to be, first I'll find the critical value also. For the critical value, I'll write T dot inverse, the probability 1 minus alpha by 2, and the degrees of freedom n is 6, k is 2 minus 1, 3 degrees of freedom. The critical value is 3.18. So my prediction interval will be the point estimate minus the critical value times. Now the problem is I don't have MSE. So let me put 1 instead of MSE. 1 will not be MSE. You know how to calculate MSE. So I'm just putting 1 instead of MSE times another bracket 1 plus square root. Yes, 1 plus this factor. And I should put a square root here. So this is the lower limit, 75 point something. And I copy this whole thing and put it here with a plus sign. And this will be the upper limit. The score is 79 point something, but we are 95% confident that score will be between 75 and 84 for this specific student. And if you're talking about all the students whose major one score is 31 and their CGPA is 3.6, what will be their average score in regression? That you will do it without 1 plus. Without 1 plus interval will be the estimate for the average. So this is the today's class. If you have any question from today's class, you can ask. Otherwise, you can go. I will, but let me make the data realistic. This data is not realistic. What? No, no off.
Why?
What do you mean by why? There should be a reason to give you off, not a reason to not give off.
Major exam. Because we check the major exam.
If I'm giving you off, then you should ask why off, not the other way. You see, if you